QCL, QVL stuff equation to master it, to solve this problem. But today, since we want to know the voltage of this 3 ohm resistor, we can just transform this kind of stuff into the standard form of the Devenan problem. So we can treat this we can cut off this branch, the 3 ohm UO branch, and the circuit will become a typical one-port linear system. So we can transform this stuff into one voltage source in series connection with a resistor, right? Let's see. We only got 6 students. It doesn't matter. Let's see. So we just transform. We just using this stuff, this method to calculate that, right? So we would like to calculate. We would like to find out what's the value of the UOC open circuit voltage. So we know that the inner loop of this one, see the current I equals to 1 and in this loop we see that we got a 9 volt voltage source and 9 ohm 6 plus 3 ohm resistance. So its corresponding current equals to 1 ampere, right? So the voltage on the 3 ohm resistor must equals to 1 times 3 ohm is 3 volts, and this one it got 6I. I is equal. I is 1 ampere, so 6 times I is is 6 volt, right? So UOC equals 9 volt. Now we would like to calculate the corresponding equivalent resistance, right? Now we have 3 ways to calculate the equivalent resistance, right? From this morning study. Then we can do it anyway. First one, we can just using the adding voltage source here and to calculate the corresponding current. So see. So now we can, using the first method, we see that the third method we have learned this in this morning. See, we can when we are calculating the resistance, we can just cut off the we call zero. We call this operation called zero. We zero this voltage source, so we just short circuited it, and we put extra voltage source here, so we can calculate the corresponding current. Then we can calculate the corresponding equivalent voltage. So we have a voltage here, and this time the 3 ohm branch is in parallel connection with the 6 ohm branch, right? So since its current is I, so then the 6 ohm branch must have a half I, 0.5 I times I current, right? And since they have the same direction, so they share the same voltage, so their current must share the same direction. So they must all goes out of this node. And the and still we see that this the voltage on the 3 ohm resistor is 3 times I, and this one is 6I. So U equals to 3 plus, from this loop we see, is 9I. And we know that I equals to 2/3 of IO. IO equals to, we know from the calculation, we saw this one is IO. IO is, so IO is 1.5 times I. So I is 2/3 of IO. So we have the U and I. So now we can calculate the corresponding equivalent resistance. So the equivalent resistance is 6 ohm. Now we have the open circuit voltage and its corresponding equivalent resistance. So the other method 2, we can just open circuit we find the open circuit voltage and short circuit current. So in this time, if we short circuited it here, and we just we short circuit here, so we left this voltage source here. So we leave it here, and we can just transform it into familiar phase. We can do it like this. We can transform it here. 9/6 is 1.5, and we have a 6 ohm resistor. So those two we could just transform them into this one, and we have this one, a 3 ohm resistor. Right, and this one is I, right? This one definitely is a 0.5 I. So I equals to 1, and 6I equals to 6 volt. So this one is 6 volt, right? So we can calculate. We already know that open circuit voltage is 9 ampere. So the current, we have this, we can calculate I is 1 ampere, and this one is 6 volt. So we can calculate corresponding. Oh, I made a mistake. 6I1 is plus 3I is 9, right? So anyway, we can still do it like this. 1.5. So this one is not 1. I made a mistake. Right. can see that this one is 1 plus goes in, this one, those two goes out. So, and we also know that 3i equals to yeah, 3 times I equals 6i plus 6i is 0, right? So we still can calculate I equals to 0. So this is the second method. Still, we calculate the short-circuited current and the open circuit voltage. So we could use their division to calculate the corresponding equivalent resistance. So we can draw the equivalent circuit. Now we transform the left side of the circuit into this one, and we put back the 3 ohm resistor branch here. So it's very easy to calculate the corresponding voltage. Obviously is 3 volt, right? So of course, if you don't, if you can master this method, you can still use the traditional way to solve it. So all this stuff, all this method we have learned, they are in parallel with each other. So, but the amount of laboring is a little bit different. So if we choose the cunning to do it, you're gonna save us some a lot of labor. So when we are dealing with the calculation of the equivalent resistance, no matter what kind of a method you choose, if you put an extra source, or you just use the open circuit short and the short circuit method, it doesn't matter. We should choose the most suitable way to apply the calculation. So to reduce the labor of calculation. So let's see another example. So we have this kind of a circuit, and we have a resistor RL here. It's 5 ohm, and we would like to calculate the power consumed by RL. So it's very easy to calculate. That is, we will calculate the current and the voltage on it. Then we can calculate that, right? And in the meanwhile, we don't want to know what was the distribution in other of the current and voltage on the other branch. So obviously, we should cut off this part and treat the the rest part of the circuit as a one-port linear system, and we can use a Thevenin system, Thevenin theorem, to transfer it into a voltage source in series connection with a resistor, right? So we cut off the corresponding part of it. Then we can transform this, we can calculate it directly, and we can also, this time we just don't recognize it, so recognize this one, because we can easily put it back to calculate that, so we don't calculate it now, right? We only consider this part of it, so it's gonna be easier to calculate this one. So we can just transform this one into another state. So we're using the traditional way to transform this parallel connection with of this control source and its resistor into a series connection of here, of this one. And we leave this control branch in. So we can calculate the corresponding, you'll see, right? We can use the KVL to calculate that. Then we should calculate the equivalent resistance. So we can using the open circuit voltage and the short circuit current method. So we just short circuited it, right? In this time, obviously, I1 equals to 0, right? Because it's been short circuited. So no current will go through this branch. They all go through this branch, right? So since this branch has no resistance at all, so and 200 times of I1 equals to 0. So we don't have this one. We don't have this one. So all is left is 50-50 ohm and the 40 volts and this branch. So it's very easy to calculate this one. It's 40 over 100 is 0.4. And the equivalent resistance could be calculated like this, right? 10 over 0.4 is 25 ohm. Now we put back the branch of 5 ohm branch, and we add back the voltage source we have here. So instead of course you can do this calculation by putting back this 50 volt voltage source, but it's going to be less convenient to calculate that. So we cut this branch and we put back this 50 volt voltage source here. So it doesn't matter. And still we have this one from the Thevenin theorem, and we have this simple, very simple circuit, and the total voltage source could equivalent to 60 volt voltage source, and the total resistance is 25 plus 5 is 30. So the current IL is equals to 2 ampere. And the voltage on it is, actually we should not use that one. We can use this I square times R. So I is 4, and I square is 4, and the R is 5 ohm. So we can use this one to directly solve this problem, right? Are you following? I think those two examples not very complex, right? Those two examples not very complex, so we continue. So in this example, we have a linear system with a with source inside. So it has its inner power supply, and once we switch switch one connected to this network, we have a current of 2 ampere, and once we connect S and 2, the port 2 and the S port, and we can measure 4 volt 4 volt voltage here. So now we would like to know we would like to know when we switch this to port 3, and what will this voltage U be? So we would like to the value. We would like to know the value of this voltage U. So when we switch to 1, it means that we short circuited this network. So it means that the short circuit current is 2 ampere, and when we switch it to switch 2, we have this this voltmeter to measure this open circuit voltage. So it's equals to 4 volt. So we can just calculate the corresponding equivalent resistance equals to 4 over 2 is 2 ohm. Then we can just transform this linear system into using Devenon theorem to transfer it into a simple voltage source. Right? So this part is equivalent to Devenon system. So it's very easy to calculate this the voltage of this U, since we already know the current is 1 ampere, and this one got 1 times 2 is 2 volt, and this one is 5 volt, right? So U equals 2 plus 5 times 1 ampere and plus 4 volt is 11 volt. So this example is it's not very complex. But in the future, we're gonna encounter something just like this, but a little bit difficult, a little bit complex, but more complex. But the basic idea is still the same. So when we're dealing with a linear system, we can using this kind of a method to only measure is open circuit voltage and the short circuit current. But sometimes the short circuit current is not very easy to achieve, right? So we have to find a way to figure it out or to find a similar approach to do this trick. Now we're gonna introduce you this Norton's theorem. It's just another version of Devenant's theorem, but this time we're not using the voltage source to do the trick. This time we were using the current source to do the trick. Okay, we have 7 members. But still, it's not. We haven't reached the maximum number of our students. So we can treat this Norton theorem as another version of Devenant's theorem. So those two theorem is actually equivalent to each other. Still, for any linear one-port circuit with sources, so with source, but not this definition is a little obscure. With sources. We can we transform it into a one-port linear system with only one current source and in parallel form with a connection with a resistor. And the current of this current source equals to the short circuit current of this one-port network. And similarly, the parallel resistor has a value of the input or the equivalent resistance of the original one-port network. Here we have this network A. A is a linear system with sources inside. And we can transform this linear system into a much simpler form. One current source in parallel connection with a equivalent resistance R. But we know that Norton equivalent circuit we can just obtain it from the Devenant equivalent circuit directly, because the value of this current source is the short circuit current we calculated from the Devenant theorem. So the proof of this Norton equivalent theorem is very similar to the proof of what we learned in this morning of the Devenant theorem. So we just skip the proof. The proof is very simple. We can, right, using the proof of the definite system, we can transform a linear system like this into a definite system, and we can transform the definite system into a Norton system, right? Using the transformation of the sources, right? So it's not very complex to achieve this. So let's take an example. We would like to know the value of this current I. From the knowledge we have learned, we can just using the node voltage method to calculate it directly, right? So, but instead of that, we don't want to do that, right? Actually, from the traditional KCL and KVL function, we can also calculate that, right? In this circuit, right, we can use the mesh current method to do that, right? So, but instead of that, we don't do that. We can do it another way using the Norton, so-called Norton equivalent method. So we can treat the rest part of this branch. We cut off this branch, right? And the rest part became a one-port linear network with sources. And we just calculate the short circuit current here. The short circuit current is very easy to calculate, right? We know that I1 equals to 12 over 2. So in this mesh, so I1 equals to 6 ampere. And we can calculate that 10 times I2 plus 2 times 6 ampere, so it's 12 volts and equals 24. So we can calculate I2 is 3.6, right? Now we know the value of I1 and I2. So I see the short circuit current IC equals to the negative of I1, I2. Or we can say that their direction is different. So then we can calculate the equivalent resistance. The equivalent resistance is very simple, right? We remove all the voltage source, so we just short circuit them, where we bypass them with wire. So we have this stuff, 2 and 10 in parallel form. So we have the equivalent resistance, we have the short circuit current. Now we put back the original port. This is a node point A and point B, right? So we put back the 4 ohm branch, and the right side is the equivalent Norton circuit. So it's very easy to calculate the current I, right? Are you following? I think this example not very difficult to understand. It's quite simple. It's a lot easier than the example we have illustrated in the replacement theorem part, right? So now we have a circuit like this. This is another example. This is another example. We have this one, and we would like to know the value of this voltage source, right? And we think I think this is a quite complex uh, uh, quite complex circuit. So we can just calculate this one, the port A and B, and remove the voltage source or the current source. So we would like to apply the Devin's theorem. We would also use the Norton theorem here because it's easy to calculate the short circuit current in branch AB. Then to calculate the corresponding open circuit voltage. So let's see what was the value of the short circuit current. So we remove this branch and we can the we connect point A and point B with a wire. So we would like to calculate the corresponding ISC. So since we only have one source here, and we would like to get straight the relationship between each and every resistor. I made a mistake. We should not number it like this. We already have a point A, right? So we had better give it another name. A, B, C, D. And I have this one, E, right? So we can see between C and E, we have a 6 ohm, and A and C. We should make a table of here. So it's kind of a complex. Should do this like this. C and D. So can see that this 3 ohm and this 6 ohm are connected to one another. This time it's hard to express. In this transformed we don't have a point A any longer. All this stuff is A, right? We don't have a point B. So this is a point B, and this point C, this is point D. So between point A and B, you see, before this one is between point A and B, and this one is between point A and D, right? And together, they were between A and D, right? So 6 and 3, and this one is between A and D, right? That's this one. And for another one, another branch is, you see, this one is between A and C, and still A and D is here. See? So we have a 2, 6, and 3 here. So those two groups are in parallel with each other, and so we can have it like this one, right? So we can calculate the corresponding IC. So this one, for this circuit, we should mark all the node before we do this classification. We have to figure out the relationship between each and every resistor, who is in parallel with whom, who is in series connection with whom. So this is what we should take care of. So now we have the number of the current, short circuit current. We should get the equivalent resistance. So now we can just cut off the source, what is source here, and bypass it with a wire, right? So still, we have to remember this point is B, this point is B, right? Still, we have to figure out a way. So we can see the corresponding equivalent resistance here. So we have we can have the Norton equivalent circuit here, like this one, 3 ampere current source and 4 ohm resistance. So this is it. So have to pay attention that once we have a equivalent resistance equal to 0, then we can only have the Thevenin equivalent. There's no Norton equivalent. So in this case, if equivalent resistance is 0, so that one for that one-port network only have Thevenin equivalent. There's no Norton equivalent circuit. So this is the case we have to pay attention to. So let's take a 10 minutes break.
OK，老师。
Okay, I can see, you can see the screen, right? So let's say that again. That we have to pay attention to that. Okay, we have a newcomer. Oh, right. Let's see. For some special case, like that's like one that's we have no equivalent resistance. For example, like this one, we have a resistance equals to what equal to 0, and then we only have this equivalent Thevenin transformation, and there's no Norton equivalent circuit. So this is a very special case, but doesn't we don't encounter this scenario very often, but from time to time we're gonna encounter something like this. And the other case is that if our equivalent resistance equals to infinite, then this one-port network only has Norton equivalent circuit and no Thevenin equivalent circuit. So there's two cases. One is the equivalent resistance equal to 0. The other one oh, let's see, doesn't matter. Okay, like this one. The other one is equivalent resistance equals to infinite. So one is 0, one is infinite. When equivalent resistance equals to 0, there's only Thevenin equivalent circuit. When the equivalent resistance equal to infinite, then we only have the Norton equivalent circuit. So these are two extreme situation. But when it happens, we have to do it with like this. That's all. Now we can when we have a one-port circuit with a power supply inside, and we put some load on it. When the load has different values, the power transferred from that one-port circuit to the load is different. So we would like to discuss when would the load to gain the maximum power from the circuit, and the value of the maximum power is meaningful, has some meaning in engineering practice. So let's see, we have a network A, a linear network A is one with only one port, and we have a load here. Could be a resistor, could be a motor, could be a lamp, a light, or any other stuff. Anyway, we just call it load. And we would like to know when will this load get its maximum power from the linear system, and the value of the maximum power is what. So we can transfer this linear system into its equivalent dividend uh, form, and we can just put a adjustable resistor here to mimic adjustable load. And the power of the load on the load equals to I squared times the resistance of the load RL. And we know that this is a look this the power curve looks like this according to the value of the RL. So it did indeed it has a color is not very suitable. We see. Indeed, it has a maximum power here. So we derive do the derivation of the P the power, and we put its derivation equals to 0. Then we can calculate the point that it has of the maximum power of the P. So when the maximum power happens, the value of the load equals to the value of the equivalent resistance. So when RL, the value of RL equals to the value of R equivalent resistance, then it will reach the maximum power. And the main power equals to the square of the open circuit voltage over 4 times of the equivalent resistance. So let's see the value of this one RL when it will reach this maximum power, and its maximum power is. So let's see. In this case, we have a load R load here, and we can using this Devenant transformation to calculate it. So we can cut off this branch and do the equivalent transfer of the rest of the circuit into its Devenant form. We would like to calculate the open loop open circuit voltage EOC. So it's not very difficult to calculate that. You see that this one has the value of UR over 20. UR is a number, the value on this one, right? And we know I1 and I2 together they equals to 2 ampere. So we can say that they are 1 ampere, and we can calculate the value of UR. So we can easily calculate the corresponding open circuit voltage UOC. Then we should calculate the equivalent resistance, right? See that in this time we open circuit this branch. because it's a current source, right? So that branch is gone. And let's see this one. This branch is gone, and we just uh, put a voltage source here. And still, we know that I1 equals to I2 equals to half of the current I. So we can easily calculate the equivalent resistance. And now we know the equivalent resistance and the open circuit voltage. Then we can apply the maximum power transmission theorem. So when RL equals to R equivalent resistance equals to 20 ohm, and it could gain the maximum power, and the value could be calculated using this formula. So this is a little demonstration of how we use the maximum power transmission theorem. So it's very easy to remember that RL equals to R equivalent. So it's very easy to remember. So this is what's about the maximum power transmission theorem. And we know that something we should pay attention to. The maximum power transmission theorem is used to is when one-port circuit is given and the load resistance is adjustable. And if your load is stationary and you can't change the load, so there's no such thing called the maximum power transmission. And we also know that the so-called equivalent resistance and the power consumed by the equivalent resistance does not equal to the total power consumed in the real linear system inside that linear network. So when the load gets its maximum power, the transmission efficiency of the circuit is not exactly 50%. Generally, it will be much less. So the so-called maximum power transmission theorem is in theory, and we have to consider that the power does not have the nature of additivity. So we could add we could use the superposition theory to calculate the voltage and the current because they are linear, but we cannot using the superposition theorem to calculate the power, since the power is the current times the voltage. So it's not it is a product of the current and the voltage, and so it's not linear. When we're dealing with this kind of situation, it's easy to combine Davenant theorem or Norton theorem to calculate the maximum power problem. So we can just transform this problem into a very simple form. Now we can introduce you the Telegon theorem. The first Telegraph theorem, at any moment, with a lamped circuit with N nodes and B branches, and the branch current and the branch voltage have the associated reference direction. So it satisfies this relationship. So it's called the power conservation theorem. So the first Telegraph theorem is actually called the power conservation theorem. So the sum of the power absorbed by all branches of any circuit is always equal to 0. So we can see it like the other way is the power gives in a circuit equals to the power consumed in the circuit. So the power consumed equals to the power given. So it's actually another form of the energy conservation theorem. So let's see the proof. So see, we have a circuit like this. We have 6 branches and 4 nodes. We can apply the Kirchhoff's current law. So since we have 4 nodes, or we only have 3 independent nodes, right? So we have at least 3 ACL equation. And we apply this formula. UKAK K is from 1 to B. And we can express the branch voltage by using the node voltage. So we have U1 equals to UN1 and U2 equals to UN over UN3 and so on and so forth. And we could combine those we can combine these equations. Still, we can put it like this one. The left part of this equation could be classified into 3 factors: UN1 times this stuff, UN2 times this stuff, UN3 times this stuff. And we also know that from this one, we know that this one, negative I1 plus I2 plus I4 equals to 0. So negative I1 plus I2 plus I4 equals 0. So this one equals to 0. And also the second one, UN2 times a value equals to 0. And UN3 times a value equals to 0. Right? This one equals to 0. So 0, 3, 0 plus 0 plus 0 equals to 0. So we have proved the first one of the Telegraph theorem. Right. So this is the first expression of the Telegram system. So it's just another expression of the energy conservation theorem, but expressed uh, in the branch current and branch voltage form, just like that. So still we have to know that this stuff comes from the energy conservation theorem. So let's see the second expression of the Telegram theorem. For any time, for two lambda circuits with both with n nodes and b branches. Let's see. We should not use a capital letter. For any moment, for two lamped circuits. This time we have two lamped circuits, and they both have n nodes and they both have b branches, and their graph is identical, but consists was the content on each branch is different. And in the meantime, the branch current and the branch voltage have the associated reference direction. So they will have this requirement. So this is the first circuit, and this one is the second circuit. Then the first one has let's see that the branch voltage of UK and the branch current of IK. And the second one is branch current is IK with a height, and its voltage is UK with a height. And we exchange their voltage and current. So we make the voltage of the first group and it times the voltage current of the second, the corresponding branch current in the second circuit. It equals to 0. And also we see that we combine the current of the first one and times it with the second one, the corresponding branch, and it also equals to 0. Oh my God! So this is called the Gaussian power theorem. Gaussian means almost. So it's a French word, means almost. So this time we have this conclusion is unbelievable, right? So it's very interesting to have this one. So we have this Gaussian power theorem here. So we notice this one. The UK is from the branch from the first loop circuit, and the IK is from the second circuit. The content in those two circuits may not be identical, but their graph is their structure is identical. So we can have this conclusion. So let's prove it. First, we apply the KCL to circuit 2, right? and we calculate the first one, and we express the branch voltage with the node voltage, and we rearrange them. Still, we have this stuff. Right? Still, we have this. So, which means the constraints of the circuit uh, is from the very nature of this structure, right? And no matter what we put into it, right? So the basic intricate constraint inside of it is from its structure. So this is a very useful conclusion. Let's see a example. I think this is a little too much for you to digest, but once you go over it after the class, I think you can master it. It's not very difficult, but it's very interesting to have this kind of a relationship, right? So we found two circuit, and they have the same structure, but the content on each branch may not be same, but we exchange their the combination of their the corresponding current or current voltage and current current the branch current and branch voltage, and these will reach same conclusion. So this is very interesting. So let's see the first example. So we can also using this conclusion to analyze the society in different countries. So if two country, let's say we have two countries. Those two countries they share the same society structure, but not the same nation, not the same language, but and we can see if they have the same structure, they will have some similar behavior. Is that it comes from the constraint of the structure and not from what's inside the branch, right? So what is interesting in science is that we can apply one theory in one domain, explain another phenomena or another theory in another domain, and that still stands, right? As if we decipher the secret of the God, right? And let's see this example. See, when R1 and R2 equals to 2 ohm, and this time this one equals to 8 volt, and I1 equals to 2 ampere, and then U2 equals to 2 volts, and we would like to know when R1 equals to 1.4 ohm, R2 equals to 0.8 ohm, US equals to 9, I1 equals to 3. So what's the value of the U2, right? So we can calculate like the using this Telegram second the Telegram theorem, because we know that basic we can apply the Telegram theorem into this one as well. So we consider those two cases to be two circuits with the same structure and different parameters. So we can use the second expression of the Telegrams. So from 1 we have u1 equals to 4, I1 equals to 2, u2 equals to 2, I2 equals to u2 over R2 is 1 ampere, right? So we can calculate this one, from the first preconditions. And from the second precondition, we can calculate that u1 equals to 9 minus 3 times of 1.4 is 4.8 volt, and I1 height with height is 3 ampere, and I2 is 5/4 of times of U2 height. And now we can do the stuff, right? So we can do it like this. So we can see that we apply the second expression of the Telegrams theorem. This is the first case, and this one is in the second case, right? And we apply it by using the Telegrams theorem. We see that the other stuff, all right, I don't like. You can see that the first one equals to the second one equals to 0, right? And the third one, this one, actually is identical to the third factor on the right side of the equation. So we can just remove them, right? We just remove them, and then we just put the number in it. We can calculate U2 with a height. So without even knowing what's inside the network, we still can calculate the corresponding value of the branch. So this theorem is very useful, right? So now remember where we begin. We only begin from the Ohm's law and the very basic setup of the Kirchhoff's current law and the voltage law theorem, and now we can go this far to calculate this stuff. So what achievement we have, right? So that's the fun in doing science, right? As we know that in the past, in the Islamic world as a peak, when it was at its peak, there are a lot of mathematicians and physicians in the Arab empire, and that times the culture and the civilization of the Islamic world is much more splendid than the Christian world. When the Christian world was in the so-called the dark millennium under the church restriction, and now after that, after the first and the industrial revolution, the Western world gets stronger, and then the old world, both the Chinese world, the Eastern Asian world, and the Middle Asia world relatively fall behind, but we are still a civilization with much more longer history than the Western world, or not at least not less than them. So we are catching up, and in the future, I think the old continent, the Eurasia, especially the East Asia and the Middle East, will go back to its former glory through scientific work and industrial improvement. And this is a example of how to application of the Telegon theorem. So the Telegon theorem is very interesting, and so let's see another example, right? And see that we know that for U1 equals to 10, I1 equals to 5 ampere, and U2 equal to 0, I2 equal to 1 ampere. And we would like to know when U2 equals to 10, what's the value of U1, right? So obviously, this is a very good case for apply the Telegon, right? So we would like to know. So we see that I1, U1, I1 have the relationship is U1 dot head is I1 times 2 ohm, right? And so we can do the calculation like this. So we can write so-called Telegon equation, and we just remove the similar rest part. So just like we did in the last example, so we don't repeat that procedure again. And we know that U1 head with equals to 2 times I1 with a head. So combine those two equations, we can calculate the number of U1 head. So that's very interesting. We don't even know what's inside the network, but we still can calculate the corresponding number of the value that we would like to know. So something we should pay attention to that when we apply Telegon theorem, the branch voltage circuit must satisfy the Kirchhoff's voltage law, and the other one is the branch current is also must satisfy the Kirchhoff's current law. And when we apply the Telegon's theorem, the branch current and the branch voltage, they must take the associated reference direction. Otherwise, we need to put the negative sign into the formula. Otherwise, it will not will be have the same meaning. Since the first one, first Telegon theorem, we know that it comes from the energy conservation theorem, right? So in a closed system, right? In a closed system, all the energy emits equals to energy takes. So only one part of the circuit, some member in the circuit gives out energy, and the other members takes energy. So all the energy remains the same. The total amount of energy remains the same. We also would like we also know that the energy cannot be created or destroyed. It can only transfer from one object to another, or it can only transfer transformed from one state to another, right? So that is the energy conservation theorem. So the first expression of the Telegin theorem actually comes from the energy conservation theorem. So this is why the science is very interesting, right? As if you will have pick up, we'll take a pick on the Lord secrets, right? So that makes us could see the world much more deeply. So we can see what others cannot see. And this theorem, its correctness, got nothing to do with the specific characteristic of the components. So no matter what components you put on the branches, this theorem always stands because it comes from energy conservation theorem. So it does not concern what kind of stuff you put into the branch, and the structural constraints of the circuit already ensured the correctness of this elegant theorem. So this is what we have to pay attention to. The first one, the branch current must meet KVL, and the second one, the branch branch voltage must meet the KCL voltage law, and the branch current must meet KCL, and the branch current and branch voltage must take associated reference direction. Otherwise, we have to put negative sign before the branches, those branch who did not take a reference direction, associated reference direction. So let's move on to the so-called reciprocity theorem. The so-called reciprocity is an important property of a special kind of a linear system. So if a linear system does possess this kind of reciprocity A, so when we put we exchange the place of the input and the output, and the response under the same excitation under the same stimuli will not change. Oh my God! So this is a very interesting theorem, right? So today we have encountered several very intriguing theorem, right? So and it's kind of when we're dealing step into the scientific world much more deeply, we encountered actually it becomes kind of a philosophy, right? And we can explain our daily lives and daily events by applying those kind of theorem. So that's very interesting. That's the beauty of science. And the network who possess this reciprocity is called reciprocal or reciprocal network. This reciprocity theorem is actually a generalization of the property of the circuit, and we can apply it when we're doing the sensitivity analysis, and we can also apply it in the measurement of the technology of the network. So this is the brief generalization of this kind of theorem. So let's introduce you the first the reciprocity theorem. For a two-part